So this morning I'm going to be talking about the hidden treasures of crash reports. Okay, I'll just hit the spacebar. So yes, my name is Patrick Wardle. I am a variety of things, co-founder and CEO of a new initiative called W, focusing on building Mac security components. But most importantly, I am, as I mentioned, one of the co-founders of the Objective-C Foundation and author of The Art of Mac Malware. I remember, now 15 years ago, being in a similar position as you, a student learning about cybersecurity threats. At that time, there was really not a lot focused on macOS, so I decided to dedicate my career to that, and this has taken me all over the world, including being here today. So I want to start with a question, and the question is about crash reports, which we have a definition on the slide, and I will get into that more. But raise of hands, who here knows about, or even better, who here loves crash reports? Okay, so we have a few. That's actually very good. And my goal for this talk is to hopefully increase that number. So by the end, we all understand the value of crash reports, because they're not something people often talk about, and they are something that also are not well loved. And I'm here to change that. So I like to start my talks by focusing on what you will learn. So today, I hope we all gain an understanding of what crash reports are and also the value of them. Specifically, I hope to show you how we can use them to uncover malware, bugs, and much more. As we can see on the slide, though this talk is focused largely on crash reports, we will also touch on topics such as reverse engineering and vulnerability discovery. Now, you might be wondering, who should care about crash reports? Well, I'm here to tell you that we all should, and we should care about them deeply. We will go through various case studies, but I'm going to show you why users and developers should care deeply about crash reports. I will also talk about hackers and intelligence agencies have been and continue to be very interested in crash reports as well. And then finally, how system administrators and security teams, defenders like myself, are also very interested in crash reports. So first, and this is probably the best known, best understood case study, is the fact that users and or developers should be interested in crash reports. So we'll talk about crash reports more in detail, but the idea is when a program encounters a fault, a bug, an error, in some cases it will then crash. Behind the scenes, the operating system creates what is called a crash report. So that's what we're talking about today. And these are mostly designed for developers. I myself am a developer. If my tools have bugs, which I'd like to think they don't, but sometimes they do, only human, a crash report will be generated. And in that case, as we will see, this has all the information about what triggered the crash itself, which for me as a developer gives me the information so I can fix and improve my tool. So here's an example where I was actually the user. Students of my training yesterday, we talked about reverse engineering, and one of my favorite reverse engineering tools is a disassembler called Hopper. Hopper is great, but as is the case with any software, it occasionally crashes. So here's an example of a crash report. We'll talk about the specifics of it details, but the takeaway here is I saw that there was a crash, I got the crash report, and I sent it to the developer of Hopper via email. He was very thankful that not only was I reporting a bug, but also that I had given him the crash report, which has the information, as I mentioned, for him to figure out what was wrong with his code, what was the problem with Hopper. And then from that, he was very quickly able to fix the issue and push out a new version. So that's a win-win. It's a win-win for me as a user because now the software is more stable, right? It sucks if you're using a program and it crashes and you lose all your work. And it's a win for him because now his product is more robust. Security teams should also be very interested in both collecting and analyzing crash reports. And I love this story from Microsoft because it really reiterates the value of crash reports. And yes, we're talking about crash reports on macOS, but they're generated on every operating system, and conceptually, they are basically the same. So all the way back in 2008, Microsoft was already collecting crash reports from Windows systems. And what they would do is when they would get them, they would rank them by the commonality of their occurrence. And they mostly were doing this to fix bugs. So if they pushed out an update and Windows systems started crashing, there would be a lot of crash reports of that one type that then they would analyze and quickly fix. However, they noticed at number 45,000 in the ranking, there was a crash report that had only happened twice across all of the tens or hundreds of millions of Windows systems around the world. So very, very rare. However, as the story on the slide explains, when they started to analyze this, they figured out that the crash report was generated from a failed exploitation attempt. So a lot of remote exploitation will exploit what are known as memory corruption vulnerabilities. We're not really going to get into all the specifics of that, but the takeaway is that memory corruption vulnerabilities, especially when they are remotely exploited, are not usually 100% successful. And what happens when they are not successful? The program crashes, which means a crash report is generated. So what Microsoft did is they ingested this crash report and they analyzed this and they realized, whoa, this is something kind of crazy. Turned out the attackers had found a zero-day vulnerability, meaning it's a vulnerability that nobody else knew about, including Microsoft. And this vulnerability affected every version of Windows. And when they successfully exploited it, which they did most of the time, they got system-level, essentially root-level access on Windows systems for anywhere in the world. So this is like God mode. This is like the vulnerabilities that keep Microsoft up at night and the vulnerabilities that hackers love and yearn for. So from the crash report, Microsoft was able to figure out what the bug was that they hadn't known about before and then push out a patch that meant users around the world were now protected. So again, great story showing the value of crash reports to defenders. Crash reports on iOS are also a big hit. There's been some examples of startups that have been focused on analyzing crash reports on iOS. On a mobile platform like iOS, where you often can't run other security tools, ingesting crash reports is a great way to detect malware and/or failed exploitation attempts. So again, in the iOS space, their value is very realized. I also want to mention that crash reports can help you uncover malware. Some examples of this, if we remember Stuxnet, the world's greatest computer virus, targeting computers in Iran, was ultimately uncovered because it had a small vulnerability or issue, bug in it that would cause computers to crash. This then led to its discovery. More recently and more specific to macOS, we have various malware samples that, unfortunately for the malware, crashes on certain versions of macOS. And the idea here, or the reason, is that malware is often not written as well as, say, operating system vendor software. Malware authors are, first and foremost, hackers, maybe not software engineers. So they might not test the malware as much as legitimate products. Also, malware is often doing kind of funky things. It's pushing the envelope. It's invoking private APIs. It's trying to stay hidden. So because it's operating more in this gray field, this gray range, it's almost by definition more likely to crash. So as defenders, this gives us an opportunity, if we are collecting and ingesting and analyzing crash reports, to perhaps discover malware on systems that previously was undiscovered. Recent example is Zuru. We can see at the time it was undetected. It wasn't flagged by any of the antivirus engines. However, on certain versions of macOS, it would crash. So if we were looking at crash reports, we would detect something funky that we didn't recognize was running on the system, which would have revealed the presence of this otherwise undetected malware. On the trend of malware, it's also important if you're a malware analyst to understand crash reports, because as I mentioned, they often show you what is wrong with the program that is crashing. So here's an example. The infamous Lockbit ransomware group recently started porting their ransomware to macOS, but it was buggy. It would run a little bit and then crash. This was good for Mac users because it meant that they were essentially not impacted yet. But for malware analysts and security researchers such as myself, I actually wanted the malware to run to completion in a virtual machine so that I could analyze its actions fully and then also test my detection tools. So what I had to do was look at the crash report, figure out why the malware was crashing, patch it for research purposes only to make sure it could then run so that I could test my security tools to say, yes, they would detect it even if it was functional. So again, I was able to do this because I was able to understand and read crash reports. Finally, hackers and intelligence agencies should be, and in some cases are, very, very interested in crash reports. So the NSA, which is the US government's, one of the US government's spy agencies, supposedly was using crash reports. I used to work there. I can't specifically comment on this, but this is from leaked documents to the media, which claims that the NSA was using Windows error messages. The headline says to spy on people. It's not really true. What they were doing, according to the media, was to analyze the crash reports that were being sent to Microsoft to do two things. First, and we will see this, crash reports contain a lot of specific information about the system where the crash occurred, including the operating system, the service pack level, the language settings. And if you're also trying to remotely infect or exploit that system, that fingerprint information is super, super important. Also, if you are an intelligence agency or a hacker collecting these, you can see what's crashing on those systems. And maybe those are crashes that you could exploit yourself. So this is a little hard to see, but I love this leaked image because it was from an internal presentation from the National Security Agency. And what they did is they took the Windows error reporting pop-up and they photoshopped their own text. And it basically says, this information may be intercepted by a foreign SIGINT system to gather detailed information or better exploit your machine, which I think is hilarious, and it's essentially them admitting that crash reports are very valuable. And they were able to do this because at the time, the crash reports that were sent from computers to Microsoft were not encrypted, so they were able to, using their interception capabilities, grab those. And then finally, crash reports are really the source of ultimate truth. So a few months ago, I'm sure many of you are familiar with this, Windows users woke up to their computers crashing continually. It melted down the tech world, right? Flights were grounded, hospitals couldn't perform operations. Everyone was like, what's going on? And immediately, everyone started blaming Microsoft. They were like, Microsoft, your software sucks, it's breaking. And this was kind of understandable because it was Windows systems that were crashing. Well, turns out Microsoft was not to blame. A company called CrowdStrike was. And how did we figure this out? We figured this out by looking at the crash report. However, even with the crash report, some people got it wrong and started wildly tweeting theories about what they thought went wrong. And I included this tweet because it was liked over 100,000 times and retweeted over 25,000 times. But it got the underlying issue completely wrong. Even though it had a screenshot of the crash report and circled a few things, it was totally wrong. So what we were able to do, though, by analyzing the crash report was to actually get the facts right. We were able to confirm, or rather predict, exactly what went wrong before either CrowdStrike or Microsoft came out with the details. So if you understand crash reports and know how to read them, you will get, like I said, kind of the absolute source truth. And you can combat, in some senses, misinformation. All right, I'm going to now jam through some crash report basics. First and foremost, what are crash reports? As I mentioned, they're basically files that are created when a program crashes. MacPaw has written some great articles about that. The main takeaway is they're not really created for the everyday user, so we have to spend some time articulating what they contain. On macOS, you will find crash reports in the diagnostic reports directory, or you can use the console to get a list of them. Their file extension is .ips. OK, I'm going to do a brief demo. We're going to have some buggy code, and then I'm going to walk through the crash report that's generated so we can understand the components of the crash report. So when we're analyzing other crash reports, we're able to understand exactly what is going on. So we have some buggy code. I am basically declaring a pointer, but I'm setting its value to null or 0. I then dereference or try to access the memory that that pointer points to. But as many of you know, if you try to access memory address 0, that's invalid. That is going to crash. It's known as a null pointer dereference or a null pointer exception. So when I compile this, this is valid compilable code, and run it, we can see that, no surprises here, it crashes and generates a crash report. If we open the crash report, we can see some basics, including the information about the process that crashed, also the version of the software, which is helpful. Sometimes you have different versions of your software, and so it's good to know which version crashed. And then also information about the operating system, and a timestamp, which is helpful as well because sometimes certain operating systems are affected, whereas other cases, others are not. If we look more into the crash report, we can see that it tells us what thread crashes. Most programs are multi-threaded, so it's very important to know what thread actually caused the fault or the crash. In the case of a simple command line application, like the one we are demoing here, there's only a single thread, so that one is identified. We then have exception types in code. This is information from the operating system that provides some basic information about what crashed. Here we can see that there was a bad access, which makes sense, remembering we're trying to access memory 0, which is invalid. And we can actually see in the exception code that it says there's an invalid address at, and then gives us the memory address 0. So already we basically have understanding of what exactly went wrong. Thread 0 crashed, trying to access invalid memory at 0. So a null pointer exception. Now, the next part of the crash report, which is very important, is the stack backtrace. So this shows us the sequence of calls that got to the bug. And this is really important because a lot of times there may be multiple paths to get to the faulty code. So we need to know exactly which one was taken. Also, the last frame in this crash report is something known as the faulting instruction. This is the address of the actual executable code that caused the fault. And this is important because this is often where, and I will show you, we begin our analysis, because this is, again, the instruction where the exception occurred. So with that basic understanding, let's now look at some actual examples that impacted macOS, and we will get more practice and learn more about the crash reports as we go through these. Now, the first question you might be asking is, how does one get information about crash reports? How do you collect crash reports? And that's a valid question. If you are a system administrator, perhaps you have access to lots of systems. Maybe you can just gather from them. I don't have access to such computers, so I am stuck to using crash reports on my computer. But good news, macOS crashes a lot, which generates crash reports. So I love this screenshot because in the middle, I am creating a tool called DNS Monitor. DNS Monitor is a network extension that I write. It allows you to track DNS traffic, to uncover malware, et cetera, et cetera. And I had a bug in my code. Not perfect. However, when my code crashed, two interesting things happened. First, it crashed a tool called NSLookup, which is an Apple tool I was using to test my tool. And then behind the scenes, Apple's network extension session manager, which loaded my tool, also crashed. And we can see here, those are both system components. So this was surprising. I mean, I wasn't that surprised my tool crashed, especially I was in the middle of developing it. But then I was surprised that this triggered apparently other issues or vulnerabilities in other components of macOS that crashed. So that was, again, like kind of annoying, but at the same time, as a security researcher, I was very excited because it now means I have crash reports that I can analyze. And I'm sure all of you, if you look in the crash report directories on your Mac, you will find crash reports either from system components or applications on your system. So I want to talk about some examples of crashes I found that were interesting to me, and again, will give us more information about crash reports. So Yara is a third-party library that is used in a lot of security products because it allows you to match on sequences of bytes. So it's kind of like an antivirus pattern matching tool. So again, you'll find it in a lot of important security products. I was testing it, running it in one of my products, and I noticed that on certain versions of macOS, at certain times, it would crash. If we look at the crash report, we can see it's crashing with a code signature invalid error, which is very strange because my tool was validly signed. So what I did is I looked at Yara's implementation, and it's open source. That was really great. And then I look at Apple's private closed source implementation of the library, and I noticed that it was slightly different. So the first thing I did is I took the crash report, and this pointed me to the line of code in Yara's library, right? So I found the faulting instruction, went and looked to what that mapped to in source code, and I saw it was triggered, or basically was a result of how they mapped files to scan. So the idea is you load a file into memory that could be malware, and then Yara will scan it to see if it matches, say, a known antivirus or known malware signature. And the way Yara was doing it, they were mapping it in with just the map private flag. The way Apple was doing it, we can see in their disassembly, is they were mapping it with this map resilient code sign flag. And what I did was I did some more research on this flag, and it turns out that if you are scanning a unsigned or invalidly signed binary on macOS, even though you're mapping it into your own process to scan, not to run, you have to use this Apple-specific flag. Otherwise, macOS will detect that you are accessing unsigned or invalidly signed memory and crash. So very subtle, very nuanced, very Apple-specific bug. So with this information, I was able to submit a bug report to Yara, and Yara was really happy because I think other people had run into this, but it was it happened so randomly, and most users aren't digging into crash reports. They didn't understand what exactly was going on. So I was able to provide a crash report telling them not only what was going wrong, but also what the fix was. So we can see the developer said, OK, interesting stuff, very complete, and then a few days later pushed out a new fix. So this is great. So Yara is now invoked with mmap using this Apple-specific resilient code sign flag. We can see the patch here, which means it no longer crashes. So this is great. The developers of Yara are stoked. Me as a user is stoked. And then Mac users around the world that are relying on security software that uses Yara are now more stoked because that software is not going to crash. So big check, big win for crash reports. The next one happened in the kernel. Again, I was developing a tool, but my tool only ran in user mode. I would run it, go out surfing, come back, and my computer had panicked. And I was like, this is annoying, but I get excited when my computer crashes because it means maybe there's something interesting going on. So if we look at this, we can see that there is a faulting address which points to unmapped memory. Also here in the extended instruction pointer, we have the address of the function or the instructions that cause the crash. If we take that address and map it to disassembly, we can find what the code is doing is it's looking at an address to see if it's 0. Now this part of the kernel is open source, so we can then map this faulting instruction. Again, this is where the exception occurred that panicked the system. We can then map that to more readable C code, and we can see what they're trying to do is check if a path is null terminated. This is a common operation. You often have a sequence of bytes, and you want to see if there is a null termination at the end, so you can treat that sequence of bytes as a string. Now, the problem is, if you look very closely at the faulting instruction, what they're doing is they have this path variable, and they're using its length to check the last byte. But the problem is they have a very subtle error, and that is arrays are zero-based index. So if you actually go to the length of it, you're going to be 1 byte outside, as we see here, meaning you have what is known as an off-by-1 error. You're going to read 1 byte outside the array. Now, this normally isn't a problem unless the address or the next page of memory that comes right after that array is unmapped. And in the kernel, if you try to access unmapped memory, you are going to cause a panic. So this is a standard, very traditional off-by-1 error in the kernel. So I reported this to Apple, and we can see the comment in their code says, make sure the path is null terminated. Their fix was to add a string copy call. And if you know about string copy, what does string copy need? It needs a null terminated string. But there's no guarantee that this string is null terminated. They were trying to check it in the previous version. So Apple's fix actually made everything worse because a string copy will keep copying until it finds a 0. This means if the kernel memory that comes after it does not have a 0 in it right away, they're going to start randomly copying and leaking kernel memory, which can contain all sorts of very sensitive information. So Apple's fix was actually to make the problem worse by introducing what is known as an information leak. And then finally, while Apple was trying to get the fix correct, I went back and said, hey, your fix actually made everything worse. I decided to look a little bit more into the code of this function and actually found an even more problematic bug, which was an exploitable kernel heap overflow. This is a bug that could allow an attacker to elevate their privileges and get arbitrary code execution in the context of ring 0 and the kernel. So the takeaway here is a simple crash report actually revealed a ton of very interesting issues, ultimately leading to a very nice exploitable bug. This next bug was also revealed by crash reports, and it's an important bug to me. We'll see why in a second. So I have a friend, she's from Taiwan, and so we were chatting, and I like to send people emojis, just like my thing. And she said, Patrick, every time we chat, like, my phone crashes. And I was like, that's weird. And she's like, are you hacking me? And I was like, that's rude. One, I would never hack my friends. And two, if I did, come on, my hacks don't crash. So I said, OK, what's going on? And she showed me every time she would type Taiwan, her phone would crash. And she's like, is China trying to hack me? And I was like, I don't think so, but let's dig into that. So I grabbed the crash report from iOS, and we can see if we look at the stack backtrace that in it, there's code related to the core emoji framework, which made sense because it was when an emoji was involved. If we look at the implementation of Apple's code, again, we can get this information from the crash report. We can see that they are trying to load something that is supposed to be in the x21 register. But if we look at the x21 register at the time of the crash, from the crash report, it is null. And what do we know? If you try to access null memory at 0, it's going to crash. So they have a null pointer dereference. And the question now becomes, why? So we need to dig a little bit more. So if we look back in the code right before the crash, we can see what they're doing is getting the locale of the phone. So they're basically saying, what are the language settings of this phone? However, the problem is they don't check that this succeeds. And this API call that gets the language or the locale of that phone can sometimes fail, which in that case means they return null. Now, null pointer dereferences are usually not that interesting. They're not exploitable. But what was super interesting here is what they were looking for. So after they get the locale, they are comparing it with CN. CN is obviously here, China. So what Apple was trying to do was detect if the version of iOS or the phone was in China, and if so, not show the Taiwanese flag. This is because in China, the Chinese government doesn't essentially recognize Taiwan, and so they went to Apple and said, no, don't show the Taiwanese flag. So what this bug actually revealed was actually Apple had acquiesced to the demands of the Chinese government and added censorship code to iOS to suppress the Taiwanese flag. And unfortunately, well, that's not bad enough. That code had a bug which would cause a crash on certain scenarios. So again, from the crash report, we could confirm that Apple was indeed censoring certain components of the user's activity, again, because of the Chinese government. And then the last one I want to talk about is a very recent bug impacted Apple's network extension manager. Basically, they had some issues where if a security tool was loading, it would cause a crash. And on the next slide, we will learn exactly what went wrong. What they are trying to do is print out an error message. Here we can see that the error message they are trying to load, they're saying it's a format string, and the format string should have a %@, %@, %@, %s. At runtime, these are filled in with different values. A %@ means an Objective-C object. A %s means a C string, just the sequence of bytes. It's very important that if you say you're going to have a %s, you give it a %s. However, if we look at the format string that they get back, what do we see? The last format string variable placeholder is not a %s, it's a %at. So what this means is it led to an object type confusion issue, which would crash the Apple's network extension manager. We can confirm this in a debugger. We can see that the format string they got indeed ends in %at entitlement. But what they are trying to fill it with is a %s or a C string. If you pass a C string to something that is expecting an object, it will crash. And the problem with this is not so much that it was an exploitable vulnerability in the sense that it would allow you to execute arbitrary code. No, what it could do, though, it could allow untrusted or unprivileged code to take down this component by crashing it, which then in turn would unload all other security tools that were running on the system. That's not good. OK. Now, I could talk about crash reports all day. These are crash reports on my box. We can see there's crash reports from virtualization, from the Windows server, from payment message extension, all sorts of very interesting things. And again, if you look on your Mac, you will probably find some very interesting crash reports as well. OK, takeaways, because we're about to run out of time. First, crash reports should be your best friend. They allow you to find bugs and to, in some cases, fix or exploit them, and also uncover malware and exploits. So again, we're going to end. Raise of hands. Who here now loves crash reports? OK, great. Awesome. We have made many improvements. So that is a wrap. Again, I just want to thank all of you for attending my talk. Again, I want to thank my colleague Andrea for helping organize this, MacPaw, Moonlock, and for all of you for being here. So thank you again.
Thank you, Patrick. You did change at least my attitude to crash reports. So guys, if you have any questions, please raise your hands, and I will give you the mic, and you will be able to ask what... Nobody?
We have one.
Oh, yeah, I see.
So in one of the slides, you had a GIF of someone typing Taiwan to your friend, but then you were talking about how the emoji would cause a crash. Was the same thing that was causing it to crash with Taiwan the same thing that was causing it to crash with the flag?
Yeah, that's a great question. So that was actually my friend who said that I was crashing her phone, and I was a little skeptical. So I went and actually saw her type, and on iOS, when you type a word, it often auto-suggests emojis. So in that case, when she typed Taiwan, it would trigger the suggestion that should normally have the Taiwanese flag. But when iOS went to render or display that flag, it would crash. So the bug actually happened anytime any app or any piece of iOS attempted to render or show the Taiwanese flag. So if I sent a message with it, when her phone went to render that message, it would crash. If she typed Taiwan and iOS suggested that as like a emoji swap, it would crash. Any app, Signal, WhatsApp, browser. And so it was something very problematic. Again, not exploitable, but again, revealed Apple's censorship logic that was buggy. Thank you for your question.
Did you get an answer?
Yes.
Yeah, great. Anybody else? I will look here. No? Nobody?
I must have explained it so well.
Yeah, it must have been that.
I will also
Thank
be
you so
around the
much.
rest of the day and the happy hour, so if you want to chat more about reverse engineering, Mac malware, clearly I love this stuff. I would be super stoked to chat with you more. So thank you again very much.
Thank you.